Let's look at OpenStax University Physics Chapter 6, Problem 43. Two blocks are connected by a massless rope as shown below. The mass of the block on the table is 4 kilograms and the hanging mass is 1 kilogram. The table and the pulley are frictionless. A. Find the acceleration of the system. B. Find the tension in the rope. C. Find the speed with which the hanging mass hits the floor if it starts from rest and is initially located 1 meter from the floor. So let us get organized here. Let's write down our knowns and unknowns and then look at the diagram some more and draw on it. So we know that the block on the table is 4 kilograms and they called that M1 in the diagram. So M1 is 4 kilograms. And the hanging mass is 1 kilogram. So that is M2 is 1 kilogram. We know that the pulley and the table are frictionless, so I'm going to write mu equals 0 just so that I remember that. And in part A, we want the acceleration of the system. So I'll just say A is equal to question mark. In part B, I want the tension in the rope, so I will call that T equals question mark. And in part C, we want the speed with which the hanging mass hits the floor if it starts from rest. So we know that V initial is 0 for mass M2. We know that it's located at a height of 1 meter above the ground initially, and we want the final velocity, we want the final speed with which mass 2 hits the floor. All right, so now let's look at the diagram. We see that we have two masses, M1 and M2, and we're told that M1 is moving to the right with acceleration A1, M2 is moving down with acceleration A2. We see that there is a string that connects the two. So since we have two masses, that means that we have to identify the forces acting on each of the masses. So our object of interest are M1 and M2. So let's start looking at M1. Now, since the mass has a mass, that means that there will be a gravitational pull from the Earth exerted on this mass. And we call that gravitational pull close to the Earth the weight. So that means that M1 is experiencing a weight going down like this. So this is my W1. Now, if you're just sitting there holding a pencil and you drop the pencil, then the gravitational pull makes that pencil go down, right? But when we look back at this mass, we know that this mass won't just fall down due to the weight, due to the fact that the Earth is pulling down on it. So why doesn't it fall down? Well, because it is supported by this table. So that means that this table will exert a force upward on M1 to balance this weight that the Earth acts on it with. So that means that there is a contact force between the table and the mass, and we call that the normal force. So I have now the weight and the normal force on mass 1. Now get in the habit of using subscripts for everything. So since I'm dealing with mass 1, I used weight 1, I'm also going to use force normal 1. It is possible that it's unnecessary, but it is a good habit to use all the forces that act on mass 1 with subscripts 1. It's going to be easier to differentiate between the different objects that in the problem. All right, so if your laptop is on the table, right? A weight acts on it and the table holds it up. Now, your laptop won't spontaneously move to the right just if these two forces acting on it. The reason your laptop would move to the right is if something pulled on it to the right. Well, in this situation, since we have a rope here, that means that the object will be pulled to the right by this rope in the direction of the acceleration. So this force here is called the tension force, And again, since it acts on mass 1, I'm going to call it tension 1. Now we're told that there is no friction, so that means that all the forces acting on mass 1 are these three forces: the weight, the earth pulling down on it, the normal force, the table holding it up, and this rope pulling it to the right. So we're done writing the forces that act on mass m1. Now let's look at mass m2. Again, since it has a mass, that means that the earth is going to pull down on it. That force is called the weight. So I'm going to draw weight, and I'm going to call it 2 because it acts on mass 2. Again, back to your pencil. If you drop your pencil, it will accelerate down with an acceleration equal to the acceleration of gravity, so that would be 9.8 meters per second squared. But if you tied your pencil to a rope and lowered it, then your pencil will not fall down with the acceleration of gravity, but it will have a different acceleration just like this object does. So the point of this rope here is to lower the object down rather than let it fall under the acceleration of gravity. So that means that this rope is going to exert some force, and remember that ropes always exert pulling forces. So it's going to pull up on mass 2, so I'm going to call the tension in this rope T2. Now, M2 is not in contact with any other surfaces, so there is no contact force, there is no normal force, and I think we are done with drawing forces on mass 2. Now, to simplify diagrams, we like to draw free body diagrams. I'm just going to call it FBD for free body diagram. And I'm going to start with mass 1. So here I have mass 1, and I'm only going to draw the forces acting on it. So I know that there is weight 1 going straight down. I know there is normal force, Fn, I called it 1. And there is tension 1 going to the right. So these are the three forces acting on mass 1. What about mass 2? So here is my mass 2. And I have weight going straight down, so I call this W2. And I have tension 2 going straight up. And those are my two forces. Now, it is a very good practice to use the direction of the acceleration as your positive x-axis. So the direction of motion of the objects will be your positive x direction. So plus x direction is direction of motion. So I'm going to draw this as my positive x, and perpendicular to it, I'm going to have my positive y. And now this might throw you for a loop, but since the acceleration is down for m2, this will be my positive x, and positive y would be perpendicular to that in this direction. So use the direction of the acceleration as your positive x direction, because it will come in really handy when you have to figure out directions, pluses and minuses, on your forces. All right, now there are a few other things that we know. We are using here a rope, and the rope is massless. So we also can assume that the rope will not stretch. In the case of a massless rope, a massless pulley, frictionless pulley, a rope that does not stretch, the tension in the rope everywhere in this rope will be the same. So tension 1 and tension 2 are actually the same. So let me write this down. Tension 1 equals tension 2. Then we also know that the two masses are going to travel together. So M1 is going to go to the right, M2 is going to go down. And since the rope won't stretch, then the acceleration A1 and A2 are also going to be the same. So I'm going to have A1 equals A2. I just wrote them as scalars, not as vectors, because it's easier for us to picture it as directionless, especially since we have tension 1 going to the right and tension 2 going up. So these guys are in opposite directions, really. It's simpler to just have T1 and equal T2 in magnitude and A1 equals A2 in magnitude. We'll have to pay attention to directions. All right, so now that we know all of this from the diagram, we have to see what exactly it is that we're looking for in the problem. So in part A, we want the acceleration. Note that the problem didn't say find the acceleration A1 or find the acceleration A2. They asked for the acceleration of the system because there is a single acceleration of the system. So let's try to figure out how to find the acceleration. Well, we know that by Newton's second law, sum of the forces on any object is mass times acceleration. And these are vectors, so I'm going to write them in vector form. Now, I have two different masses, and one of them has forces in two different directions. So I'm going to write Newton's second law for each of the masses. So for M1, I have sum of the forces in the x direction on M1 is M1 times, we called it A1 in the diagram. Now the forces that act on M1 in the x direction, so the x direction is to the right, we only have a single force acting to the right, and that is tension 1. How about I just call it tension, is equal to mass 1 times acceleration, because I said A1 equals A2. So that's all I can write for mass 1 in the x direction. Now I can also have sum of the forces in the y direction for mass 1, and that would be mass 1 times the acceleration 1 in the y direction. And we see that in the y direction, so perpendicular to the table here, the object doesn't move at all. So there is no acceleration in the y direction here. So we can say that this thing is 0. So that means that the two forces that act, I have the normal force being in the positive y direction, the weight being in the negative y direction. So then I have Fn1 minus W1. So Fn1 minus W1 equals 0. So I wrote Newton's second law for object M1 in both x and y directions. Now, I can't get much information from just block 1. I will write some of the forces in the x direction for block 2 as well. So x direction for block 2 is down. Positive is down. So that means that W2, weight 2, is going to be positive, whereas tension 2 is going to be negative. So then Newton's second law in the x direction for block 2, which says that it's M2A2, will become W2 minus the tension, remember that T1 equals T2, is equal to mass 2 times acceleration 2, but A1 equals A2, and I just called it A. So now I have these two equations with two unknowns. How about I take T from here and plug it into there? So that means that W2 minus, so T is M1A equals M2A. I know that weight is mass times G, so W2 is M2 times G. And if I add M1A to both sides, I end up with M1 plus M2. I'm also factoring out A, so I get this expression. What I'm looking for is A, so A will be M2G divided by M1 plus M2. So the acceleration of the two blocks is going to be, what is M2? 1 kilogram times 9.8 meters per second squared divided by 4 kilograms plus 1 kilogram. And to use sig figs, we end up with 2.0 meters per second squared. So the acceleration of the system is 2 meters per second squared. It is to the right for mass m1 and down for mass m2. All right, now in part B, we're looking for the tension. And we already have this expression written out, or this expression written out, where we have tension in the equation. When we were doing part A, we didn't know tension and acceleration in both of these equations, but now we know the acceleration, so we can use this equation to find the tension. So tension is m1a, and I'm going to rewrite it in a symbol form because I rounded to get 2.0 meters per second squared for the acceleration, and I don't want to compound my uncertainty here. So I have m1, which is 4 kilograms, times m2, which is 1.0 kilograms, and then 9.8 meters per second squared, divided by 5.0 kilograms. It's m1 plus m2. And when we plug these numbers into our calculators, we end up with 7.8 newtons. So here we have the tension that pulls m1 to the right and holds m2 up, so it only accelerates downward with 2 meters per second squared rather than 9.8 meters per second squared. All right, now part 3 is asking us for a velocity, actually for a speed. And in Newton's laws, we have nothing to do with speeds. So we have to draw back to our knowledge of kinematics to find the speed. So here we were given the initial speed of m2 was 0, it was stationary. We know how high above the ground m2 was, and we're supposed to find the speed with which it hits the ground. So now that we found the acceleration in part A, we can use v squared equals v naught squared plus 2a delta y. And I called it delta y because I am going to redefine my x and y axes for this part because we're used to using kinematic equations in x and y direction, and y direction is just vertical. So I'm going to use the positive being up and the negative being down in the y direction, just the way we did in chapters 2 and 3 in the book. So I'm looking for the final v, the velocity with which it hits the ground. And since it's down, and I just said that I'm going to pick up as my positive the way we did in the kinematics problems, that means that the velocity is going to be negative. So when I take the square root of both sides here, so I'm going to have square root of this and square root of that, I end up with v being negative square root of v naught squared plus 2a delta y. Again, it's negative because it's down, and this is how we solved problems with kinematics. So that will be negative square root of 0 meters per second squared plus 2 times. So now the acceleration is down. A2 is down. So I'm going to use negative 2 meters per second squared, the way we did with kinematics. And delta y is final position minus initial position. So final position is 0 when it hits the ground. Initial position is the 1 meter that we were told that mass m2 was above the ground. So when we plug in the numbers, we end up with negative 2 meters per second. So this is the velocity. This is v final velocity. But we're only looking for the speed. So we want the magnitude of this. So that means that v final, the speed, is simply 2.0 meters per second. And here we have the solution to this problem.